Time travel, as a concept, has fascinated humanity for centuries. While it has often been the subject of myths, literature, and science fiction, the modern scientific discussion began with Albert Einstein's theories in the early 20th century. According to Einstein, time is not a constant, but rather relative. This means that time can move at different rates depending on speed and gravity. This idea revolutionized our understanding of the universe and introduced the possibility that time travel, in some form, might be possible. Einstein's special theory of relativity, 1905, and general theory of relativity, 1915, laid the foundation for understanding time travel. Special relativity introduced the concept of time dilation, which asserts that the faster an object moves, the slower time flows for that object relative to a stationary observer. The faster you travel, the more pronounced the time dilation becomes. This is described by the time dilation equation, which shows that as an object's velocity approaches the speed of light, the difference between time experienced by the moving object and the stationary observer grows exponentially. For example, an astronaut traveling close to the speed of light would age much slower than someone on Earth. This is a fundamental principle of time travel, as it suggests that, in theory, traveling close to the speed of light could allow an individual to move forward in time much more quickly than others. Another aspect of Einstein's theory, general relativity, expands this concept by introducing the influence of gravity on time. In regions of strong gravity, time moves more slowly. This is known as gravitational time dilation. The closer an object is to a massive body like a planet or star, the more its time is slowed down. For instance, time moves much more slowly near a black hole compared to Earth. If someone were to orbit a black hole, time would appear to pass much slower for them than for an observer far away. This phenomenon is another form of time manipulation, though in this case, it is more about the effects of gravity on the flow of time rather than travel in the traditional sense. The concept of time travel as we understand it today often invokes the idea of traveling backward as well as forward in time. Theoretical pathways that could allow for such time travel include wormholes. Wormholes are hypothetical tunnels through spacetime that could, in theory, connect distant points in space and time. The concept of wormholes was first suggested in the framework of Einstein's general relativity as an Einstein-Rosen bridge, where two black holes are connected through a tunnel. This theoretical tunnel could, in principle, allow for time travel between distant locations in space or even between different times. However, the wormhole concept is fraught with uncertainty. Most theoretical models suggest that a wormhole would collapse before anything could pass through it, meaning it would be impossible for humans to use them. Some have proposed the idea of a traversable wormhole that could remain open long enough for objects or people to pass through. But such a wormhole would require something called exotic matter, a theoretical form of matter with negative energy that could counteract the gravitational forces pulling the wormhole closed. To date, no exotic matter has been discovered, making the creation of a traversable wormhole seem highly unlikely. The notion of time travel also leads to several well-known paradoxes, the most famous being the grandfather paradox. This paradox arises when a time traveler goes back in time and prevents their grandfather from meeting their grandmother, thereby preventing the time traveler from ever being born. This creates a logical contradiction. Such paradoxes challenge the idea of time travel, and physicists have proposed various theories to resolve them. One such theory is the many worlds hypothesis, which suggests that every time a change is made in the past, a new, separate timeline is created. This would mean that any actions taken in the past would create a new version of reality rather than altering the original one. Another possible resolution is the self-consistency principle, proposed by physicist Kip Thorne. This principle suggests that the laws of physics would prevent any time traveler from creating a paradox. For instance, if you tried to go back in time and kill your grandfather, some cosmic force would intervene to prevent the paradox from happening. In this view, The universe enforces a form of self-consistency that makes paradoxes impossible. Beyond the theoretical models, there is another intriguing possibility involving closed time-like curves, CTCs. These are solutions to Einstein's equations that create a path in spacetime that loops back on itself, allowing an object to return to the point in time where it started. Such closed time-like curves could, in theory, permit time travel, though they would require extreme conditions, such as the presence of rotating black holes, Kerr black holes. These rotating black holes are thought to create regions where closed time-like curves might exist, though the physics of such regions remains largely speculative and untested. Quantum mechanics, the branch of physics that deals with the subatomic world, adds another layer of complexity to time travel discussions. Concepts such as quantum entanglement and quantum tunneling suggest that particles at the quantum level behave in ways that defy our classical understanding of time and space. For example, quantum tunneling allows particles to pass through barriers that they would not be able to cross according to classical physics. Some physicists have speculated that quantum tunneling could provide a way for information, or even particles, to travel through time. The many worlds interpretation of quantum mechanics proposes that every quantum event creates a new timeline, further suggesting the possibility of parallel timelines that could be affected by time travel. Despite all the theoretical frameworks, there are still massive challenges to making time travel a reality. The most significant issue is the enormous amount of energy required to manipulate space-time. Creating and maintaining a wormhole, for example, would require energy on a scale far beyond our current technological capabilities. Similarly, traveling close to the speed of light requires an immense amount of energy, which presents a significant hurdle for any kind of practical time travel. Time travel has been a popular subject in science fiction, with works like Back to the Future, Doctor Who, and The Terminator exploring various interpretations of the concept. These stories often play fast and loose with the scientific details, but they provide an engaging look at the human desire to explore the past or future. The exotic matter needed to stabilize wormholes remains purely hypothetical, with no experimental evidence to support its existence. Without it, the idea of a traversable wormhole remains a tantalizing but unreachable possibility. Furthermore, the potential causality violations that come with time travel, such as the grandfather paradox, raise significant questions about the fundamental laws of physics and whether they could be violated by time travelers. The many worlds interpretation, MWI, of quantum mechanics proposes that every quantum event splits the universe into different versions, each corresponding to a different outcome. If time travel were possible at the quantum level, it could also lead to the creation of alternate timelines. In conclusion, while time travel is a fascinating and complex subject, it remains speculative and far beyond our current technological capabilities. Theories involving wormholes, time dilation, and closed time-like curves offer potential pathways for time travel, but practical obstacles like the need for exotic matter, vast amounts of energy, and the resolution of paradoxes make it unlikely to happen in the near future. As our understanding of physics deepens, it is possible that time travel could shift from the realm of science fiction to scientific reality, but for now, it remains one of the great mysteries of the universe. Thanks for watching. If you enjoyed this video and want to dive deeper into more exciting science topics, make sure to hit that subscribe button. Don't forget to turn on the notification bell so you never miss an update. See you in the next video.